Dear students, welcome to s.mathguru classes. So, our main discussion already we discussed some problems about partial derivatives. Next, we consider Euler's theorem on homogeneous function. Euler's theorem on homogeneous function. First, we have to know what is homogeneous function. The definition is that homogeneous function definition, a function f of xy is said to be homogeneous of degree n in the variables x and y if it can be expressed in the form x to the power n pi y by x or in the form y to the power n pi x by y. So if we express in the form x to the power n pi y by x, this is called a homogeneous function of degree n. Or we can express in this way also, y to the power n pi x by y. If we write x to the power n, then x in within bracket x in denominator. If we write y to the power n, then y in denominator. This is the rule. And what is the power of x? N. So this is called a homogeneous function of degree n. Degree n. Now how to express this? Suppose x square plus 2xy plus 3xy plus y square, this one given. So this one, this degree 2, this is 1 plus 1 2, this is degree 2, all the terms their degrees are same. If all the terms their degrees are same, so this is a homogeneous function. Now we write in this way, from all the terms taking x square common, then we get here 1, here 3y by x, and here we get y square by x square. We get this. And this equal to x square. This is within the bracket we get y by x form. So this we can write phi y by x. Y by x form we write in short form phi y by x. So this is a homogeneous function. If we compare with this, then power of x is n, here is 2, so and y by x same. So this is a homogeneous function of degree 2. This one degree 2. So again, if we consider another example, x cube plus 3 x square y plus 7 x y square plus y cube. Suppose this problem is given, and this term whose degree is 3, this is 1 and 2 3, this is 1 and 2 3, and this is 3. All the terms their degrees are same. So this can be expressed in the form of, suppose x cube common, we get 1 3y by x 7y square by x square plus y cube by x cube. We get this. So we get this again. If we multiplying by x cube, then this is x cube into 1 x cube, this into this 1x cancel, x square 3x square y, and this is 7x y square, and this is y cube we get. If we multiplying, we get this one. So this can be written as, and this within bracket we get y by x form. Y by x form. So we can write phi of y by x. Phi of y by x. So this is a homogeneous function of degree 3. This one. So same, if we consider from this, if we taking y square is common from this, y square common, then here we get x square by y square 3x by y plus 1. Or we can write y square pi x by y. So this is also homogeneous for degree 2, this form. So if any function which can be expressed either this form or this form, this is called a homogeneous function of degree, this is n, this is degree 2, this is degree 3. So this is the rule how to find degree of a homogeneous function. Now let us consider the Euler's theorem. Euler's theorem on homogeneous function. If f of xy be a homogeneous function of x and y of degree n, then x del f del x plus y del f del y equal to n f of x comma y. So this is our Euler's theorem of homogeneous function. So this function given, if f is a homogeneous function of degree n, then if we differentiate f with respect to x multiplying by x, differentiate f with respect to y multiplying by y and adding, then we get degree into function. This is our Euler's theorem. Now we want to prove this Euler's theorem. This is most important for exam. Any engineering exam, this is most important. This is important to the power infinity, most important problem. State and prove Euler's theorem on homogeneous function. This will come in this way. State and prove means you have to write this question also. So proof, we consider this. Here given f of xy is a homogeneous function, since f of xy is a homogeneous function of degree n. Therefore we can write, f of xy we can write x to the power n pi y by x, because by definition of homogeneous function, if any function which can be expressed in the form of this is called homogeneous function. Now what is the power of x? N, the degree n. This is the homogeneous function. Now our aim to prove this. First we differentiate this one with respect to x. Now del x of f, del x, x to the power n pi of y by x. This is product of two function. I recall the product of two function, ddx of fx into gx. This is fx ddx of gx plus gx ddx of fx. This is our product rule. First function ddx of second function ddx of first. So here first function ddx of second plus second function ddx of first, we get this one. By using product rule we get this one. Now this one x to the power n, again you know this formula, ddx of f of x equal to f dash x. When you get f dash x, if both x same, within bracket x, this x, both are same, we get f dash x. But within bracket is y by x, this is x, these are different, this is not possible to write f dash x. So using chain rule, this is y by x. So this one I have written del, actually you should write del x, not ddx. This is del x. This. So this will be del y by x into del y by x del x plus phi y by x, this is n x to the power n minus 1, this one, and this will be x to the power n phi dash y by x, and this is y is constant, del x of 1 by x phi y by x n x to the power n minus 1, and this is x to the power n phi dash y by x. This y we write here, y here, and this will be minus 1 by x square phi y by x n x to the power n minus 1. So we get this will be, this is power 2, this power n, we can write x to the power n minus 2, and this one minus front side, we write minus front side, and y phi dash y by x plus n x to the power n minus 1 phi y by x, we get this. Now this is our del f del x. Now if we multiplying both side by x, because in our answer x del f del x, if we multiplying both side by x, then we get x del f del x, and this is multiplying by x minus x x to the power n minus 2 y phi dash y by x n x x to the power n minus 1 phi y by x, and this implies x del f del x, this n power is 1, this power minus 2, so ultimately you get x to the power n minus 1 y phi dash y by x. So this is power plus base are same, minus 1 plus n minus 2, then n minus 1 again, and this is nx x n x to the power n phi y by x, we get this result. So from this we consider this is number 1 and this is number 2. Again we differentiate this one partially with respect to y. Again if we differentiate partially with respect to y, what we get? Del f del y. This is del y x to the power n phi y by x. This implies del f del y x to the power n is constant, because we differentiate partially with respect to y, x is constant. So we write del y phi of y by x. This is x to the power n del phi y by x del y by x del y by x and del y, using chain rule, because if both are same then we write phi dash x, then this and this same, x to the power n phi dash y by x, and this is 1 by x constant, and del y is 1. So we get x to the power, this power is 1, n minus 1 phi dash y by x. This is del f del y. Now if we multiply both sides by y, because here y is given, therefore y del f del y x to the power n minus 1 y phi dash y by x. This is number 3 we consider. Now we consider left hand side. In our left hand side, x del f del x, y del f del y, and x del f del x is this value, putting this value minus x to the power n minus 1 y phi dash y by x plus n x to the power n phi of y by x, and Next, y del f del y. Del f del y means this one plus x to the power n minus 1 y phi dash y by x. And these two are like terms, this will be cancelled. Finally, we get n x to the power n phi of y by x. And this means f of xy. This means we know x to the power n phi of xy means x by y by x means f of xy. So we get f of xy. This is result we get from 1. Using 1 we get this. Now what we get in left hand side this, right hand side we get this. Therefore what we get, x del f del x, y del f del y, n into f of xy. Hence proof. This is the proof. So what is the problem? The theorem is that f is a homogeneous function of degree n. Then if we differentiate f with respect to x partially and multiplying by x, with respect to y partially and multiplying by y and adding, we get degree into function. Degree is n and into function we get right hand side. These are Euler's theorem. This is most important for exam. We consider one simple problem, very easy problem, very interesting problem, whether you can believe or not, but this is easy. If u equal to tan inverse x³ plus y³ by x minus y, show that x del u del x plus y del u del y equal to sine twice u. We have to show this one. So we want to solve this problem by using Euler's theorem. Here u equal to given tan inverse x³ plus y³ by x minus y. This implies tan u equal to x³ plus y³ by x minus y. This implies tan u equal to, from these two taking x³ common, we get here 1 and here y³ by x³. From these two taking x common, 1 minus y by x. Again if we multiplying by x³ into 1 x³ cancel y³, x into 1 x and x cancel, we get this. And this will be tan u equal to this 1x is cancelled, x square 1 plus y³ by x³ divided by 1 minus y by x. So this can be written as tan u equal to x square phi y by x, because this is in the form of y by x, we write whole is phi y by x. Now what is the power of x? Power of x is 2. So this is a homogeneous function of degree 2 because power of x is 2. So this is degree 2. So tan u is a homogeneous function of degree 2. Therefore, since tan u is a homogeneous function of degree 2. This is a homogeneous function of degree 2. Therefore, by Euler's theorem, we have what we have by Euler's theorem. Now what is the Euler's theorem? We know Euler's theorem, f of xy is a function of degree n. Then if we differentiate f with respect to x multiplying by x and y into del f del y equal to degree into function we get. These are Euler's theorem. f of xy is a homogeneous function of degree n, and we have x del f del x plus y del f del y equal to degree into function. But here tan u, f means tan u is a homogeneous function of degree 2. Therefore, by Euler's theorem, we have x del x tan u plus y del y tan u equal to degrees to 2 into tan u. We get this our Euler's theorem. Tan u means f, so x del f del x plus y del f del y, degree into function. Degree means 2, function means tan u. We get this. We get this one, but actually we know this formula, dx of tan x, then this is sec square x. When you get sec square x, if this x both are same, we get sec square x. But here is tan u, here x, these are different. Here u, here y, these are different. So using chain rule, if we using chain rule, then x del tan u del u del x, del u we write extra, this cancel, ultimately we get this. And here also y del tan u del del y equal to 2 into tan u. We get this. Now these two are same, u is same, so here u is same, and here also u is same, tan u. So this can be written as x, ddx of tan x means sec square u del x. This is sec square u del y to tan u we get, and dividing both sides by sec square u del x y del y, this equal to 2 tan u by sec square u. We get this. Now 2 tan means sin by cos, and 1 by sec means cos square, and 1 cos is cancelled, we get 2 sin u cos u. This is sin twice u, and this is the proof. We know this formula, sin twice a equal to 2 sin a into cos a. So sin twice a 2 sin a cos a, so 2 sin a cos a means sin twice a, 2 sin u cos u means sin twice u. Therefore what we get? Therefore we get x del u del x, y del u del y equal to sin twice u. This is the proof. We get this one, x del u del x, y del u del y equal to sin twice u. Hence, short. This is the proof. Very easy. Consider another problem. If u equal to cos inverse x plus y by root x plus root y, show that x del u del x plus y del u del y plus 1 by 2 cot u equal to 0. So when you get this type of problem, this is nothing but our Euler's theorem. We solve this problem by Euler's theorem, because in Euler's theorem we know this, x del u del x, y del u del y, this type. Now solution is that u equal to given cos inverse x plus y by root x plus root y. This is our u. This implies cos u equal to x plus y by root x plus root y. This implies cos u equal to x common y by x, and from these two root x common 1 plus root y by root x. Again you know x by root x means root x. So x by root x we get root x. Root x we get. So 1 plus y by x, 1 plus root y by root x. We get this one. And this can be written as this x to the power half. Root means power half. And this whole you can write phi y by x. So what we get? Cos u is a homogeneous function of degree 1 by 2. This x to the power something phi y by x. This is a homogeneous function. So since cos u is a homogeneous function of degree 1 by 2. This power of x is 1 by 2, so degree 1 by 2. Therefore, by Euler's theorem, we have. Now, what is Euler's theorem? I recall this. If f of xy is a homogeneous function of degree n, then if we differentiate this one partially with respect to x and multiplying by x, then y del f del y, degree into function, you know, degree into function, x del f del x, y del f del y equal to degree into function. So here function is cos u. Cos u is a homogeneous function of degree half. Therefore, by Euler's theorem, we get x del x cos u, y del y cos u equal to degree into function. Degree means half, function means cos u. We write this. Again, we know this formula, ddx of cos x. This is minus sin x. ddx of cos x minus x. If x same, we get minus sin x. But here u and x different. We can't write this formula. So using chain rule, this u must be here, then we can write this formula. So this implies x del cos u del del x plus y del cos u del y del y. This is del u using chain rule, del y equal to degree is half, and function this right hand side cos u. So we get this one by using chain rule. We get this because if x same, we write this formula, but this u same, then we can write formula. Otherwise here not possible. U and x different, we can't write this formula. This is x del x of cos means minus sin u del x, and y, this is ddx of cos means minus sin u del y 1 by 2 cos u, and dividing both sides by minus sin u, x del x, y del y equal to 1 by 2 cos u by minus sin u. We get this. Dividing both sides by sine, we get this. And this is x del u del x, y del u del y, minus here half cos by sine is cot, cos by sine cot. And taking this one in left hand side, then we get x del u del x plus y del u del y 1 by 2 cot u, this equal to 0. And this is the proof, x del u del x, y del u del y equal to half cot u, hence short. Yeah, so there students, these are very nice, very easy, very simple. So I hope you are all enjoying with me of Euler's theorem. Euler's theorem is nothing, just practice, and you have to know the main formula. So I hope you are all enjoying. If you are all enjoying with me, then please like this video. If you are new in my channel for getting new videos at the very beginning, then please subscribe my channel and click the bell icon. Thank you.